So the kinetic molecular theory is what we use to explain the behavior of all matter that we already study in research. Solids, liquids, and gases are both covered. We're interested more in the gases right now. So there's some other information that's already given to you. You don't have to worry about writing it down. But basically, it explains the matter, properties of matter based on particles that are constantly in motion. So all those molecules and atoms, they have some energy to them and they're moving. That energy of motion is called kinetic. That's why the K is in there, kinetic. And of course, it deals with molecules and atoms. And it's our explanation, that's our theory, how it works. So, specifically, we use something called the ideal gas model to explain gas behavior. It's the ideal gas. Later on, we'll talk about a law that deals with ideal gases, but for right now, we just need to use a little bit of an understanding of what an ideal gas is and how we use it to explain the behavior of gases. So, it's an imaginary gas, an ideal gas. It doesn't exist. It's a figment of the imagination of some scientists. But we have established what these ideal gases' properties would have. Real gases, of course, are not ideal gases, but they behave like ideal gases under certain conditions. As it turns out, the conditions we normally encounter gases are those conditions that we would run into. So they very much behave like an ideal gas under the conditions of temperature and pressure that we typically study gases on. So why would we want to consider ideal gases? Well, it comes down to the math of it, really. Ideal gas math is really easy. Real gas math, not so much. So to make things easier for us to be able to kind of simplify how we do and study and be able to measure and predict things, we use these models to our benefit. So the key for this one, though, is when do real gases not behave like an ideal gas? Well, high pressure, because the gas molecules are forced to be close together. So they'll start to interact with each other a little bit more. They'll have some more attraction to each other. And at low temperatures, because at low temperatures they're not moving as fast. So when they collide, they're going to be probably able to be attracted and interact with each other quite a bit. So high pressures and low temperatures, that's the key. All right, so here's some assumptions about an ideal gas. First of all, they are made up of a huge number of particles moving around, buzzing all over the place. They are far apart compared to their actual size. Sorry if that came up kind of small. But an enormous number of tiny particles. You know, we're talking mole-sized stuff. Times 10 to the enormous numbers of particles running around. But the particles themselves are super tiny. Atoms and molecules are tiny, but there's huge distances between them. Collisions that they have, when they run into each other or they run into a surface, are considered elastic. And in elastic collision, there's no loss of energy. Whatever energy went into the collision is the energy you get back when you bounce off from that collision. So there's no loss of kinetic energy. In real systems, there might be a tiny little bit of a loss, but not much. Our third assumption about ideal gases. They are in continuous, rapid motion. Those particles are going to be moving all over the place, bouncing into each other. We're going to see a little simulation that kind of shows them moving around, bouncing around.
Want these?
Oh, those happen in Savile? Happy ball. That's an elastic collision. It hits, bounces, energy is returned. Energy hits, and it's returned. Uh-oh. Not so elastic. So, just a slight difference in the material. They look an awful lot alike. So, gas particles, they are more elastic. They like to bounce off, go places. There are no forces of attraction or repulsion in an ideal gas. And we have some gases that come close to that. Our noble gases. Well, they don't like to react with anything. So they're pretty close to that. But we do have some gases that are kind of polar, that have some charges. So there might be some attraction and some repulsion. But an ideal gas, don't have to worry about it. There's no attraction, no repulsions happening. And the last one, number 5 here, is the average kinetic energy. That word again, kinetic, coming back. Average kinetic energy is really the temperature that we measure of the gas. How fast those particles are moving. So it's the speed of the particles and another thing that's going to be combined in here when we look at kinetics. So here's the equation. I think you have to write that one down. The equation for kinetic energy is 1/2 the mass times velocity squared. I know. 1/2 m times v squared. So there's 2 components to kinetic energy. The mass of those particles and how fast they're moving. So what if you have 2 different gases, but they have the same temperature? What might that imply? Well, if they're 2 different gases, you know they're going to have different masses. So one of them has to be going faster, and the other one has to be going slower if they're going to get the same temperature. So if they're at the same temperature, they have the same kinetic energy. So our lighter particles, the ones with less mass, are going to be traveling faster to have that same kinetic energy. Bigger molecules are going to be not going as fast. So light particles move faster, heavier particles move slower, if they're at the same temperature. That's also kind of an important part there, at the same temperature. So these are the conditions in which we look at ideal gases. And for the temperatures and pressures, we look at real gases. We really kind of see that. That's really kind of what real gases do, like carbon dioxide and oxygen and nitrogen, hydrogen and chlorine and all the different gases. They all kind of follow this general guidelines. It's only when we put them under high pressure or get them down to low temperature that they start to not follow these rules so much, or be aligned with them at least. All right, so gas properties. Some of the things that we're interested in with gases. First one, expansion. Most of this is already written down there for you. Solids and liquids, their particles are really close to each other. Solids are pretty much locked in place. Liquids, if you give them enough energy, they kind of can start moving enough that they can kind of slide around each other, but there's still a lot of attraction that are holding them really close to each other. Gases, though, can fly apart. They can get away from each other. They will take up at least 1,000 times the distance of the size of their particles will be how far apart they are from each other. It could be a bit more than that. The key thing with that is then, since gases can fly apart from each other, they don't have a shape. They only will take the shape of whatever container they're in. So they will expand out and fill whatever container you put them in. No definite shape to it. That's similar to like a liquid. A liquid doesn't have a definite shape. It's whatever shape, it'll take the shape of whatever container you put a liquid in. Solids, they have a definite shape. Their atoms are locked in place. So the volume of a gas is mostly empty space. Lots of space in between those particles. There's no pieces of matter in between them. That volume is mostly empty space. And one thing to remember, when we talk about gases expanding, don't get confused and think it's the actual gas molecules that are getting bigger. They're not. It's the distance between the particles that is expanding and getting bigger. That's a common mistake I see a lot of people make when they talk about expanding gases. Oh, the oxygen molecules are getting bigger. No, not. The space between the oxygen molecules is getting bigger. Number 2, fluidity. Number 2 is fluidity. So we got lots of space for things to move around. That means that gases, their particles can go around each other. They go past each other. They can bounce off of each other. So they flow around each other easily. Gases, like liquids, are then fluid. They are fluids. It's a common mistake a lot of people make. Think that the only thing that can be a fluid is a liquid. I guess it's because it rhymes. But gases can flow. They are fluid. Another thing, they got low density. Since we got lots of empty space, we just got a small amount of mass for those gases in a large space. That means our density is going to be very low. Because remember, the density equation is mass divided by volume. That's not on here, but hopefully you guys have learned that over the years. So compared to a solid or a liquid, gases' density is incredibly low. A lot of times we measure it slightly differently, using different units, like liters instead of milliliters or cubic centimeters of volume. Because it's a lot of volume that those gases take up with just that small amount of mass that they have. All right, we're almost done. We got compressibility. Another thing that gases can do is you can compress them. You can squeeze them down into a smaller space. Anybody in here do any scuba diving? Done some scuba diving. Awesome. One of my best friends from high school is a scuba diver. And if you could not take an entire room of air and squish it down into a tank on your back, you could only go underneath the water for maybe 15, 20 minutes. Because you can take an entire room of air and squish it down into one tank that you can carry on your back, you could be underneath the water for a couple hours. Convenient. But it's all because gases can be squeezed down and compressed. Those gases have that huge amount of space between them, so we can force those gas molecules to get closer together. So we can force those molecules to be closer. But because of that, gases do not have a definite volume. We can change the volume of a gas, how much space it takes up. You can take up an entire room, or we squish it down into a small little bottle. Can't say that it has that absolute that volume every single time. It can be tweaked a little bit. So some other things that can change the volume of a gas are temperature and pressure. That's really what we do. We use pressure to squeeze gas molecules closer together in order to compress them. But also temperature can have an effect on it too, which we'll get to. And the last one, diffusion and effusion. Diffusion and effusion. So diffusion is the mixing of gas particles caused by the random motion. If I had like a thing of perfume over here, a cologne, and I sprayed it in this corner over here, eventually the people right here are going to start smelling it. And then after a little while, the people over here will start smelling it. And eventually the whole entire room is going to be able to smell it. That's diffusion. It's all concentrated in one area, but those molecules are moving, so they're going to hit into each other, and they're most likely going to be hitting into each other, and not air molecules, and eventually they'll spread out and move around the room and eventually fill up the entire room. It's because of that random, constant motion of those atoms and molecules that allows that to happen. Effusion is the movement of those gas particles through a tiny little opening, tiny little doorway. Because those atoms are moving around, they can find their way. Eventually they're going to bounce around. Eventually they're going to find that opening and they're going to make their way through it. Here's the key for both of these, diffusion and effusion. Smaller particles are moving faster. Remember that kinetic energy? If You're a smaller, lighter particle, you've got more speed to you. So you're going to find your way through other molecules faster. So you'll mix faster, so you'll diffuse faster, and you're more likely to be able to find that tiny little opening faster. Here's kind of an example. Diffusion's got that little disc with a little hole in the middle. So that the gases on one side are slowly making their way through. It looks like the purple ones are getting their way through and the green ones are making their way through there. Another example, this would be diffusion. So you've got this little spigot kind of in the middle, stopcock in the middle, and you got oxygen on one side, hydrogen on the other. Ooh, this would be a good rocket lab. Open it up and eventually they're going to mix together. Notice which one seems to be moving the fastest. Which one seems to have gotten over to the other side a little bit quicker? And the hydrogen, which is a lighter gas. So it's faster, it's going to fuse and diffuse much more rapidly. Eventually, you get kind of an equal amount on each side. Just going to happen naturally. All right, pressure. So we talked about compressibility. We can put pressure on a gas and kind of squeeze it down and get into a smaller volume. So how do we measure that and how do we talk about pressure? Well, the definition for pressure is it's a force over an area. So it's a force applied over an area. So the equation would be force divided by area is what pressure is equal to. Force divided by area. So as we apply a force over a specified area, we can calculate how much pressure is being applied there. When you go walking out on ice and you start hearing it crack, what's the thing you should probably do?
Start running.
Jump up and down really hard?
Yes.
Get up on your tippy toes? Lie down flat. That's the big thing to do. Because your weight is your force that's being applied to the ice. So that's your force. But your area is only the bottom of your feet. Very small area, so you've got a large pressure being applied to the ice. If you lay down flat, you spread your weight over a bigger area, so your pressure on the ice becomes less. If you start slipping on ice, what should you do as far as walking goes? Kind of get up on your toes.
Not going.
Right on the ball of your feet. More pressure allows you to be able to stick to the ice a little bit better.
Get up on your toes and on the ice. It looks like a turkey.
So here's a neat little example. The same weight, the same brick, has the same weight, but one way it's laying down kind of flat. So it's got a larger area, 0.1 square meters. So when you take the weight and divide it by its area, you get 1,000. We'll talk about the unit here in a second. But if we take that brick, we flip it up on its end. So now that same weight is being applied to a smaller area. So 1/10 the area it was before. So look at that increase in that pressure. It goes from 1,000 up to 10,000. It's a big difference. So units of measuring pressure. There's a lot of them. That's the bad news. There's a lot of units for measuring pressure. The one that we're going to be kind of interested in, one of them anyway, is the SI unit, which is newtons over square meters. So this will be a derived unit of measurement. And a newton divided by a square meter is what we're going to call a pascal, pascal of pressure. 1 pascal would be 1 newton over 1 square meter. The symbol for it is just a capital P small a, PA, for pascal. But a pascal is really, really small. That's not much pressure at all. Maybe about the same pressure as kind of a larger paperclip in your hand. That would be about what kind of pressure 1 pascal would be. That's not much. So we typically bump that up to kilopascals. 1,000 pascals. KPA. You ever had to inflate tires? There's usually two main pressure units, PSI and kilopascals. Those would be the two big ones. Some other units you might run into. The atmosphere, or ATM. It's not going to give you money. I hate to tell you that. Big breaking news. ATM is atmosphere of pressure. Millimeters of mercury, which of course is abbreviated mmHg for millimeters of mercury. That would make sense. We have torr, which is abbreviated torr. Great abbreviation there. Pounds per square inch. If any of you are interested in going into meteorology, there's another unit you should probably, well, two at least. Instead of millimeters of mercury, if you ever listen to the newscast and listen to the weather forecast, they'll talk about inches of mercury. It's the same thing. It's just, instead of millimeters, we use inches. But another one for like tropical storms like hurricanes is something called bars or millibars. It's another unit of measuring pressure. So there's a lot of units that measure pressure. Well, we can't. Because some people like certain units better than others. So, we may have to make some conversions between units of pressure. Darn it. So we need some equalities between those units of measurement. Well, 1 atmosphere is basically the average atmospheric pressure of the Earth's atmosphere at sea level. So that's equal to 760 torr. So I'm going to write that one down. 1 atmosphere equals 760 torr. That also is equal to 760 millimeters of mercury. So a torr and a millimeter of mercury are same amount. They're equal to each other, yeah. 14.7 psi, pounds per square inch. So if you don't know what psi is, pounds per square inch, it's the force in pounds over an area in square inches. And the last one, our SI unit, kilopascals, 101.325 kilopascals. You just write down 101.3, that's probably good enough. So, there should be some space there for you to be able to do a conversion real quick. I hope so. Convert 8.4 psi to atmospheres. Just like any conversion, you take your given amount, which is 8.4 psi. We start off our T-chart with that. Our T-chart. Now we're going to go. Then in our other part of our T-chart, we need to cancel out units. So I'm going to take my equality units up here, 14.7. So my PSI cancels out. Put that on the bottom. And these are all up here. They're all equal to each other. So I find what is my atmosphere amount? 1 atmosphere. My units of PSI are going to cancel out. And then I do my math. Take out your calculator, plug, chug. Your answer would come out to 0.57 atmospheres. You take 8.4 divided by 14.7. So make sure you keep that in a safe spot where all those equalities are, so you can use those to be able to make your conversions if you need to. More about pressure. How do we measure pressure? I'm going to go through this really quickly because we don't really measure pressure this way anymore. We use pressure sensors nowadays, but a barometer is what's used to measure atmospheric pressure, the pressure of the atmosphere. And the barometer was invented by, this name should somewhat kind of make sense to you, except for the first part of the name, Evangelista. Torricelli. A torr, yeah. So a unit of measuring pressure is named after this person, so that makes sense. Basically what he did is he took a bowl of mercury, filled up a glass tube with mercury that had a closed end, so the end that's up there at the top is closed off. Tipped it upside down with his finger over the end, put it into that bowl of mercury, removed his finger, and saw that the mercury level dropped.
He was touching mercury.
He was touching mercury, I know. I don't know how long he lived.
Probably not.
So up in the top there's like a vacuum. There's nothing in there. And what's keeping the mercury up in the column is air pressure pushing down on that pool of mercury in that little bowl down at the bottom. And he was the first person to kind of notice that when the weather gets bad, the atmospheric pressure goes down. Low pressure tends to cause storms to occur. And when there's high atmospheric pressure, he noticed that the mercury column would go up. High pressure. High pressure we typically associate with really good weather. Here's another one. This is an analog barometer. And then you've got a kitty cat here, where apparently the atmospheric pressure is rather high today. It's kind of squished down. That shouldn't be there. Don't know why that slide ended up there. All right. Another thing for measuring pressure, manometer. It measures a gas sample, a sample of a gas. Here's what it looks like. You've got a gas sample that you apply to this kind of U-shaped tube. And that is usually filled with a liquid of some sort, sometimes mercury, sometimes it could be other things, it could be water if you wanted it to. And that gas is going to apply a pressure onto that water tube, and then you measure that height that water or liquid rises up on the other side of the tube. That allows you to be able to know what the pressure is of that gas on the other side. All right. Next thing, STP. Another abbreviation. I'm trying to remember what the old oil one was. I think it's scientifically treated petroleum is what STP stood for, but that's not this. There's a different STP. It means standard temperature and pressure. So write down standard temperature and pressure. That's what STP is. This darn thing is so dark. Standard temperature, you need to know what standard temperature is. It's 0 degrees Celsius. Or there's another one up there. 273 K. 273 Kelvin. Kelvins will become important here in a little bit.
I hate Kelvin.
Standard pressure is 1 atmosphere of pressure. So it would be 101.3 kilopascals, 14.7 pounds per square inch, 760 torr. Just remember 1 atmosphere. 1 atmosphere, 0 degrees Celsius. Not too hard of numbers to remember. 1 and 0. Don't forget what unit goes with each other. So there's the old STP, oil, or Stone Temple Pilots. Yeah. So I thought about playing the Interstate Love Song, but don't forget your STP. So now we get to the gas laws. This is the last thing we're going to cover today are the different gas laws. So there are mathematical relationships between the properties of those gases we've been talking about. What properties specifically? We're not talking about like compressibility or fluidity and stuff like that. We're talking about cool stuff we can measure. There's 4 main properties when we deal with gases. First one's volume. Make sure you write down volume. The amount of space that gas is taking up. It's an important thing to measure. Another one would be temperature. What's the temperature that the gas is at? And the third one is pressure. These are our big 3 for right now. There's another one, the amount of gas. So how many gas particles do we have? Sounds like moles. But we're not going to worry too much about that one. We keep that one kind of constant here at the beginning. Change that one.
Oh boy.
So amount of gas is going to be kept constant for the 4 gas laws we're going to look at here to begin with. It's the laws. Of course, when you have the laws, you must obey the laws. Disrespect that authority. So first law is Boyles Law. Probably one of the first laws in chemistry. Boyles Law. So the relationship is between pressure and volume. So I think you need to write that down. The relationship is between pressure and volume. So what's kept constant is temperature, in this case, and the number of particles. That will be kept constant, the amount of gas. Because we have these things in sealed containers. So the relationship is, if I decrease the volume on a gas, then the pressure is going to increase. You think of like a syringe or something like that, you can seal up the end of it. You start squeezing it down. It's going to take up less volume. It's going to be squeezed down into a smaller space. But it's going to be hard to keep pushing it down harder. It's going to have more and more pressure on it. So gas is going to exert a higher pressure. So if this is true, decreased volume, my pressure increases. That means the opposite is true as well. If I increase the volume on a gas, then the pressure is going to go down. So if I'm squeezing that syringe way down and I let go of it, it's going to pop back up, take up that original volume, and there's not going to be as much pressure on it anymore because I released that pressure on it. So in this case, our two variables, the relationship here, is kind of the opposite. When one is going up or increasing, the other one's doing the opposite, it's going down or decreasing. We call that an inverse proportion, or an inverse mathematical relationship. So its math relationship is an inverse. So whenever we take a look at a gas that's undergoing changes in pressure and volume, when we take the pressure and we multiply it by the volume, we always get the same result. Which makes sense. If I'm increasing my volume and my pressure is decreasing, that means if I multiply those together, whatever one goes up by, the other's going down by, I'm going to multiply to get the same result. So here's the equation that you need to write down. P1 times V1 equals P2 times V2. P1 V1, P2 V2. R2D2. And here's what a graph would look like if you were to have a graph of the data from a Boyles Law experiment. It's a curved line like this. Don't have to worry too much about the graph of it right now. Definitely the equation you want to have. All right, so let's take a look at the next one. The next law is Charles's law. No, I guess now we're doing an example first. Start examples. So our example is a sample. I apologize. I meant to get you guys those everything written down on there. That's my bad. In this situation, we've got a sample of oxygen at 95 kilopascal, so that's a pressure. So you need to start recognizing those units and what it is that they measure. It's got a volume of 0.045 liters. We increase the pressure to 340. What volume will the oxygen have? So we've got the equation. We can figure out what each one of those measurements is going to relate to, plug it into our equation and solve it. So that first piece of information, 95 kilopascals, that's our starting pressure. And attached to that is the volume of 0.45 liters. So that's our starting volume too. Then we know that it's changed. We changed the pressure to 340. So that's our second pressure. And now we want to know what volume will it have. So you can think about this and be able to kind of understand what your answer should look like. I'm increasing my pressure, so what should happen to my volume? Pressure increases, volume should be decreased. So we plug those pieces of information in for our equation. So P1 times V1 equals P2 times V2. Then just use algebra and solve it. So 95 times 0.045 must be that number. I divide by 340. My answer is 0.013 liters. Did it go down? Yeah, it did. Went from 0.045 to 0.013. My volume decreased. The equation works. Any questions about Boyles Law? So notice the units cancel out, kilopascals cancel out. The only thing left would be liters, which is our unit for volume. All right, next is Charles's law. Temperature and volume are what we're going to relate to each other. So when we change one of them, what's going to happen to the other one? This time pressure isn't going to change. We're going to leave pressure alone. This one, when we increase temperature, the volume increases. When I was a kid, my grandfather, he had a gas station. He was a mechanic. And I wanted to play basketball one morning in the spring. I think it was like right after school had gotten out. And my basketball was a little flat. So I went in and I asked him if he could turn on his air compressor that he used to power the lift, to put cars up and be able to work underneath cars. And he's like, I'm not going to turn it. I don't have any work that I need to do. He said, just go put the basketball out in the sun and it'll inflate. I was like, I thought my grandpa was the dumbest person in the world. Like, what? That's stupid, Grandpa. How's the sun going to get air into my basketball? But being a good kid, I went and I did it. I played around, I came back, and sure enough, it was inflated. I was like, what the heck's going on there? And then when I was a freshman in high school, in my physical science class, we talked about Charles's law. And I remember a teacher saying, like, oh yeah, in order to, his example was a dented ping pong ball. A dented ping pong ball, just get a nice pot of hot water and put it in, and it'll expand and pop it back out. I remember jumping up in the class going, oh my God, as my grandpa told me to do once. And that was very embarrassing. But it works. It works. Temperature goes up, the volume of the gas expands and goes up. More volume. Opposite is true. You decrease the temperature, it's going to deflate. This is a direct proportion, not an inverse proportion. Because this time they're doing the same thing. When one is increasing, the other one's increasing. When one decreases, the other does the same thing, decreasing. So that equation is going to look a little different. Because it's 1 divided by the other one equals a constant value. So as I increase my volume, if I double my volume, my temperature must double. And so that math is still going to be the same. So there's the equation. V1 over T1 equals V2 over T2. And the graph for this will be a straight line. A straight line. All right, time for an example real quick. Although we have a little bit of warning here. When we calculate using gases, and what we're going to be using is a temperature, we cannot use Fahrenheit or Celsius. The reason why is because Celsius and Fahrenheit have negative numbers, if you use a negative number in a calculation, you could end up with like a negative volume or a negative pressure, which is impossible. So we have to use kelvins. Have to use the Kelvin scale. So how do you get to kelvins if you have a Celsius temperature? There it is. You take your Celsius temperature and you add 273 to it. That will equal your Kelvin temperature. That's why 0 degrees Celsius for a standard temperature is 273 Kelvin. 0 plus 273 is 273. So make sure you got that equation for Kelvin written down. Here's our example. We got a sample of neon gas, and it's got a volume of 752 milliliters. It's at 25 degrees Celsius. What volume will it occupy at 50 degrees Celsius? Question? Should our volume increase or decrease just by looking at it? Should increase because our temperature is increased. First thing we need to do though is change those Celsius temperatures to kelvins. So 225 plus 273 is 298. 50 plus 273 is 323. Got to make those changes. So our first volume is the 752. Our first temperature is the 298. Got to use those in our equation. We're trying to solve for V2. And 323 is our second temperature. 752 divided by 298 equals V2 over 323. So we kind of multiply both sides by 323. Notice that our kelvins are going to cancel out. That leaves us with our volume of 815. Did it go up? It sure did. 752 up to 815. Any questions about calculating the Charles' law? Next one, Lawsons Law. He's got a weird name. I would deal with it. I like it. Well, you know, it's hyphenated. In this law, we're going to compare pressure and temperature. Volume this time is kept constant. So it's a rigid container, like a big steel container. We're not going to let the volume change at all. Expand it anyway. This is a relationship just like Charles's law. When you increase the temperature, the pressure will increase. If you decrease the temperature, the pressure will decrease. I learned this one also at the same time. I figured out my grandpa was actually pretty smart. I was in a Boy Scout trip and we were going to cook some food. One of them was going to be baked beans, and it said put the can of baked beans on the fire. Okay, I didn't do it, somebody else did. Thankfully, it wasn't me. They did not open it up first and put it on a sealed pan. All of a sudden we hear this loud explosion and everybody's covered in beans. Luckily no one was injured. It was kind of a miracle that didn't happen. So, when they say, you know, keep containers away from heat sources that are enclosed and under pressure, it's a good idea to do that. So since we still have a direct proportion relationship, the math is going to look just the same. So it's P1 over T1 equals P2 over T2. And we get a nice straight line graph again. T1 over T1 equals P2. Example, we'll go through this one really quickly. Because it's the exact same math as we would have seen in Charles' Law. So I've got Charles' Law written down. This is going to look just the same. So in this case, we got a gas in an aerosol can at a pressure of 3 atmospheres. Directions say, do not store in a warm place. Bad things can happen. So let's figure out what the pressure would end up being if we ended up getting it to that warm place. So it's the same deal. I set up my problem to substitute in my information from the problem in for those variables in the equation. My kelvins are going to cancel out in my calculation. And my answer comes out to 3.27 atmospheres. So yeah, it does increase. The pressure does increase. Not that much. 3 to 3.27 doesn't seem like that much. Last one. You didn't have to write any of that down. You're okay. We're running out of time. So it's the combined gas law. Guess what that means? Oh, you have.
I don't think it says ideal.
Oops.
So they don't. Change it to combined.
Change that to combined gas law. My bad. Thank you for doing that. It says ideal gas law. Not the ideal gas law. Combined gas law. So we will combine all the gas laws. There it is. There's the equation.
What's the concept?
You could cover up whichever one you want to in order to get the other law. So if you remember Boyles Law, we kept temperature constant. So if we covered up the temperature on the bottom here, we have Boyles Law. P1 times V1 equals P2 times V2. We cover up with pressure, we would have Charles' Law. V1 over T1, V2 over T2. Write it out another way too. If you don't like fractions, you can multiply everything by temperature. Both sides kind of do the cross multiply thing. Still, we don't have the amount of gas. Don't have to worry about the amount of gas. P1 V1 over T1 equals P2 V2 over T2. Our last example. We have a helium-filled weather balloon. It's got a volume of 50 liters at 25 degrees Celsius. What do we have to do when we see Celsius? Change it to kelvins, right? What volume will it have when it goes up in the atmosphere and has less pressure on it? And it's got a new temperature, which will be a colder temperature. You go up, it gets colder. I didn't realize we were done. Sorry. So again, we just plug everything into our equation, and we just solve for it. So here's all of our initial information from the problem. Got to change the temperatures to kelvins. Rearrange it. Notice our units are going to cancel out. We got atmospheres on top and bottom, kelvins on the top and bottom. The only thing left is liters, which is our unit for measuring volume in this case. 60 liters of helium.
Why do they say that?
My anime page.